The objective of this video is to introduce the concept of Pareto optimality. Pareto optimality is a useful way of thinking about whether a machine design is optimal in some sense. To describe what we mean by this, let's take a step back and talk about what we are trying to do when we design a motor. When we design something, whether this is a motor or anything, we have some objectives in mind. And for motor designs, these objectives typically are items such as minimizing our cost, minimizing our loss, minimizing the size of the motor, or minimizing the torque ripple. And we can also talk about objectives in terms of performance metrics, where we might be actually maximizing something. So when you're minimizing loss, you're actually also maximizing efficiency. Or when you're minimizing size, you're actually maximizing torque density. But classically, when you talk about objectives for an optimization, you are trying to minimize some function. So if you really want your objective tied to efficiency, you might be minimizing the negative of efficiency. That would be the same as maximizing efficiency. So this is a frequent trick that's used when you have a function that you would be attempting to maximize, is you consider the negative of it. So you could try to minimize the negative of torque density, which would be the same as maximizing torque density. When we talk about an objective, when it comes to a design optimization, it's always a function that we are trying to minimize. When we design the motor, we may have some combination of these objectives. We might have all of them. We might have additional objectives that I haven't listed here. But the point is that we have some goals in mind for our design. We're trying to minimize some set of performance variables. And that leads us to the question of, what does it mean to be optimal? If we have multiple objectives, how do we think about whether a design is optimal or not? And we're going to talk about this by thinking about a design that has two objectives. And what we're going to do is we'll construct a plot where we plot a bunch of design candidates in terms of how it performs on those two objectives. So suppose that our first objective is loss. We want to minimize the loss of our design. We quantify that in units of watts. And our second objective, suppose that it's torque ripple. Suppose that we're considering several different motor designs that we have evaluated. Somehow we've evaluated them. Perhaps we've used finite element analysis and we've calculated the losses in the designs and the torque ripple. We can now plot the loss of each design versus the torque ripple of each design on this graph. And I'm going to indicate each design as being an X, and I'll put a number on the X's so we can talk about specific designs. So I've labeled 7 designs on here. Remember, each of these X's is a specific design's loss and torque ripple. So let's now try to compare these designs. Let's talk about whether one design is better than another design. And the first question I have for you is design X1 better than design X2? Take a second, think about this, and pause the video, press play when you're ready to hear the answer. Well, so the answer is that we're trying to minimize these objectives, right? So we're trying to find a design with the lowest torque ripple and the lowest loss. And if we look at design X1, we can see that it has a lower torque ripple than X2, and it has a lower loss than X2. And so we can say that, without a doubt, X1 is better than X2. Let me now ask you, is X4 better than X3? And you have to say the same thing. Yes, it clearly is, because we've reduced the loss and we've reduced torque ripple. So X4 is clearly better than X3. But now I'm going to ask you something a little bit trickier. Is design X1 better than X7? And if we look at this, we can see that X1 has clearly reduced the loss, but it's increased the torque ripple. So in one objective, we've improved. Between X1 and X7, X1 reduces the loss. We've optimized that objective. But in a different objective, that is torque ripple, we've derated our design. We've made our design worse. And if we were optimizing for torque ripple only, we'd have to say that X7 is better. And so the answer to this question is, it's complicated. And the answer is now up to an engineer's judgment. How much did you really care about loss? And how much did you really care about torque ripple? Maybe if you look at this batch of designs, you'd say that X4 is pretty good because we've minimized our loss some while only slightly increasing our torque ripple. Or maybe you're firmly in the camp that X7 is better because you really care about torque ripple and loss isn't that big of a deal. So at this point, you have to defer to your design specification, to your better engineering judgment for what you want to build. You might start looking at other aspects of the design. Maybe if you look at design X7, some of the dimensions of it are very difficult to machine. Or maybe if you look at design X1, some of the tolerances are very difficult to hold that you'd require. And so what we can say from just strictly looking at the objectives is that anything along this front up here is going to be optimal in some sense. Anything along this quadrant is either minimizing our loss or minimizing our torque ripple respect to one of the other designs. And this front right here is called the Pareto front. We're going to define this a little bit more formally in a little bit. But before we do that, let's talk about Pareto, the definition of Pareto optimal. So all of these designs on this front that I've sketched in purple are considered Pareto optimal designs. And the definition of a Pareto optimal design is that a design is Pareto optimal if no other design dominates it. Okay, so what does it mean for a design to dominate another design? A design is said to dominate another design. That is, we can say design A dominates design B. And when I say A and B, I'm referring to what we have up here. So we can say, you could substitute this in to say that X1 is dominating X2. X1 dominates X2 if X1 is no worse than X2 in all objectives, and X1 is better than X2 in at least one objective. And this is equivalent to stating that X2 is dominated by X1. So if we look at our plot up here, we can see clearly that X1 is better than X2 in all objectives, or it's no worse than X2 in all objectives. It's no worse in torque ripple and no worse in loss. And it improves actually in both objectives, torque ripple and loss. So we can say that X1 clearly dominates X2. But we cannot say the same thing for designs on the Pareto front. So if we compare design X4 and X6, you can see that X4 improves in one of the objectives, but it degrades a second objective. So it improves loss, but it causes an increase in torque density. So we cannot say that X4 dominates X6, nor can we say that X6 dominates X4, because similarly, X6 improves one of the objectives. We decrease torque ripple, but we degrade the second objective. Loss becomes higher. So neither X4 nor X6 dominate each other. That is, both X4 and X6 are Pareto optimal. No other design dominates them. In fact, all designs that I've highlighted in purple are Pareto optimal because no other design dominates them. And so the definition of Pareto front is the set of all Pareto optimal designs. And when we have only two objectives, we can pretty easily depict this as we've done in this figure up here. The Pareto front is always going to be this bottom left quadrant, this bottom left front of our design space when we plot our objectives against each other. When we go to more objectives, this becomes more complicated to do. So for example, if we have three objectives, suddenly this is a three-dimensional plot. If you have more than three objectives, you just simply can't plot it. And for this reason, we're going to, in this class, be sticking to considering three objectives or less, because that is the maximum that we can visualize. And we'll talk about that a little bit more in later videos. So in summary, this video has introduced the notion of Pareto optimality. We've done this by, again, summarizing the objectives that we may have when we design a motor, with the conclusion that we are almost always going to have more than one objective. And when we have more than one objective, we have a complication in how we consider whether design is optimal or not, because it might be optimal for one objective, but be really poor for a second objective. And to handle this, we introduced the definition of Pareto optimality based on whether design dominates another design. and then talked about how to visualize this on a plot.